In 3.2, what we're going to talk about are limit theorems. So we're going to take the definition of the limit that we learned in 3.1 and apply it to several different types of, or several different sequences at once to see how we can combine them. Okay, so the first thing we're going to talk about is what it means for a sequence to be bounded. Okay, a sequence is bounded if there's a number m, a real number m, so that all the terms in the sequence, now notice we've got the absolute value there, are less than some m for all natural numbers m. Okay, now why do we do the absolute value? Basically that just says that, if you have the real number line here, and here is 0, maybe some of your terms in your sequence lie over here, the rest of them lie over there. By taking the absolute values, you essentially take these guys and flip them over to the other side so that the bound is going to be somewhere up here. Okay. As an example, the sequence 5 cosine of n is bounded. And the reason for that is because all of the terms of the sequence, if you look at the absolute value of 5 cosine of n, well, the cosine of n we know is always less than or equal to 1 in absolute value, so 5 would serve as an upper bound, or as a bound, so would 6 or anything larger than 5. Okay. So we're going to prove here in just a moment that every convergent sequence is bounded. All right. So let's think about what it means to be a convergent sequence once again. I'm going to do this on a number line as opposed to some of the other ways we've depicted convergent sequences. So this is what everybody's converging to. Okay. Well, in order to be a convergent sequence, what that means is if you give me an epsilon, then all of the sequence terms after a certain point will be between x minus epsilon and x plus epsilon. Okay, so for example, we're going to use some nice big fat ones here. The first term might be way out there. Let's make it blue. The second term may be over here. The third term might be there. In between those two bounds, the fourth term might be out there. The fifth term could jump out here. But eventually, all of the terms are going to be between x minus epsilon and x plus epsilon. Now this is true for any epsilon that I choose. So I could choose even epsilon equal to our magic number 1 on both ends. If you give me epsilon equal to 1, then eventually all of the terms from some point on are going to be in this little region here. Well, if that's true, then there can only be a finite number of terms on the outside. And so the bound that we'll have will just be related to this number x that we have, and then the numbers outside of that region. So here's our proof. We're going to let epsilon be 1, just like we said. I know that eventually, that is, there's some number k, so that if n is greater than or equal to k, all the terms of the sequence are within 1 unit of our limit. Okay? I could have chosen epsilon 1, I could have chosen to be 10, I could have chosen to be anything I wanted, but 1 just is a nice convenient number. So here's a little maneuver that we'll do to help us out. I'm trying to bound n, or x sub n. Okay? I'm going to take n greater than or equal to the number k that I have here. Well, if I want to bound it, I know that this inequality is true. So I'm going to insert a minus x there, but I can't just insert that and not adjust the value, so I have to add x at the end. Okay, now we have our triangle inequality, which says that if I throw an absolute value there, an absolute value there, make the absolute values like so, then it's less than or equal to that sum of those absolute values. Now we just said that x sub n minus x is less than 1 in absolute value, so this guy is less than 1, and so this guy plus absolute value of x is going to be less than 1 plus the absolute value of x. Now remember on our previous slide, if you remember in our previous slide, we had a whole bunch of terms in between the two limit and the lower x minus epsilon or x minus 1 up to x plus 1, but then there were a few guys sprinkled on the outside. So we're going to take those guys that are sprinkled on the outside, take the larger value, 1 plus the absolute value of x, and look to see which is the largest one of them. If m is the supremum of all those values, then all x sub n will be less than or equal to m. Okay. We have some other theorems that are going to come into play, and these are the ones you're familiar with from Calculus 2. Give me two sequences that converge. Okay, I didn't say that they converged. Oh, no, they don't have to converge. We're going to give two sequences. I can form the sum of the sequences, the difference of the sequences, the product of the sequences, and, with a little caveat, provided all of these y sub n's are less than or equal to, or are not 0, none of them can be 0 if we want to define this new sequence. Okay, so that's the little caveat there. There's a theorem that says that if I know things converge, then these combinations will converge. So if x, which is x, the sequence of x sub n, if that converges and y converges, then their sum, their difference, their product, and their any constant multiples will converge to the sum of their limits and so forth. Okay? It's also true for quotients. That's another part of the theorem here, except again, once again, we'd want to make sure that if I'm doing something like, I know the book does this, they do x sub n divided by z sub n, all these z sub n's have to be non-zero. Okay, so here's a proof, and it is the proof that x plus y converges to the limit of x plus the limit of y. Okay, so I know that these guys converge to x and y respectively. I'm going to let them suppose that that's true. Again, with these limit proofs, we want to assume that epsilon has been given to us. It's a positive number. We have to show that eventually, that is, there's some number, natural number k, so that when I take the difference between x sub n plus y sub n and x plus y, that difference is less than epsilon. Okay. Well, I know that x sub n minus x can be made arbitrarily small. Y sub n minus y can be made arbitrarily small. But that's really two terms, isn't it? X sub n minus x and y sub n minus y. So the strategy here is I know that x sub n minus x can be made less than epsilon over 2 eventually. And y sub n minus y can be made less than epsilon over 2 eventually. Okay, so let's just take, for instance, maybe when n is greater than or equal to 1 million, x sub n minus x is less than epsilon over 2. But for y sub n minus y sub n to be less than epsilon over 2, maybe I have to go past 2 million instead of 1 million. Well, and then I'm going to let k be the supremum of those two numbers, so it would be 2 million. Okay, when n is greater than or equal to k, I look at this difference. This is what I want to be less than epsilon. I rearrange the terms like I did before, x sub n minus x, y sub n minus y. I use the triangle inequality. You see that that comes up many times. This first term is less than epsilon over 2. The second term is less than epsilon over 2, so their sum is less than epsilon. Now, I did not have to choose epsilon over 2 and epsilon over 2 in both cases. I could have said, hey, I know that eventually will be less than epsilon over 10 for x sub n minus x, and y sub n minus y is going to be less than 9/10 of epsilon. Then their sum would still be epsilon. So epsilon over 2 is just a convenient one. Okay. Another theorem you're going to run across. If x is a convergent sequence of real numbers and all of their values are greater than 0, then the limit has to be greater than or equal to 0. And this makes perfect sense. We'll just illustrate this with a number line to help understand. So here's my number line. Here is 0. And all of the terms of the sequence are out here somewhere. Doop, 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 doop. Okay? There is no way that the terms of the sequence could suddenly hop over here so that this is the limit. That's a big fat X there. There's no way it can happen. And here's why it can't happen. Remember, in order for this number x to be the limit, I should be able to get arbitrarily close to x by choosing n sufficiently large. I should be able to get as close to this number as I want by choosing n large enough. Which means, if I want to get close to that, I have to pass 0. But that would contradict the idea that these terms are all greater than or equal to 0. Eventually, the terms would have to get less than 0 in order to get as close as I want to that particular number. So that's sort of the rough idea of the proof. If you read the book, they give the more formal derivation. Okay. So we're going to look at a couple of other theorems, and these all kind of tie together in order to build the squeeze theorem. Okay. You give me two sequences that are convergent, and if I know that x sub n is less than or equal to y sub n, then the limit of x sub n has to be less than or equal to the limit of y sub n. Now, in order for them to be convergent, or in order for these things to hold, maybe x sub n is always less than or equal to y, or always less than y, but the limits could be equal to each other. And let me show you an example of this. Suppose that I have here, this is what both of the limits are going to approach. Well, y might look like this. It might start off way out here, and then here, and then here, and you see it's approaching that particular number. On the other hand, x's might always be just a tad bit less than y. Maybe they're half the distance from y to that particular number. So all of the x's could be less than y, but they might both approach the same number. Okay. The next theorem is very similar to that. You give me a convergent sequence. If all of the x's are trapped between a and b, then the limit has to be trapped between a and b as well. Okay. One thing I didn't mention was the theorem up here. This theorem up here is actually proven by taking our previous result and forming a new sequence, z sub n, which is the difference of y sub n minus x sub n. Okay? Since y sub n is always greater than or equal to x sub n, or y sub n minus x sub n will always be greater than or equal to 0, so z would have to converge to some number greater than 0, which gives us that result. Alright, so here's the big guy. Not terribly surprising. It's called the squeeze theorem. You give me three sequences, and if they satisfy this inequality, x sub n is less than or equal to y sub n, which is less than or equal to z sub n, for all n. Now when I say for all n, maybe it's not exactly for all n, but for all n past a certain point. We talked about tails in section 3.1. Okay, so suppose this inequality holds if I know that x sub n and z sub n both converge, and I know that x sub n and z sub n both converge to the same value, then y sub n is squeezed between them, so y sub n has to have the same limit as the other two. And it's really just a build-up of the other theorems that we saw here. We'll give an example of this. I'm going to show that the sequence 3 plus sine of n over n converges. Okay. Well, this is sort of like the tip-off that the squeeze theorem might be in order. When you have a sine or a cosine, that tends to happen. Okay. I know that the sine of n is always -1 or larger. So if I replace sine of n by -1, I'm going to end up with something smaller or maybe equal to that particular value. Okay. On the other hand, sine of n is always less than or equal to 1. So if I replace this sine of n by 1, we'll have sine of n is less than or equal to 1, and so we end up with 3 plus the sine of n over n is going to be less than 3 plus 1 over n. Now these two limits we can figure out. Limit of 3 minus 1 over n is 3. Limit of 3 plus 1 over n is 3. These can be done using some of the theorems that we talked about earlier. Since those two limits are equal, this limit has to be equal as well.